Hello everyone and welcome to the third part of our mini series where I'm going to try and apply the principles of constraint dynamics, rigid body simulation on this little system that I saw in a video by Andre the Great, of course. This is a fixed dimension bar fixed by its pivot to the origin and another bar free to rotate pivoting around this bar, and disk that is rolling without slipping on this bar, which is with constant dimensions, and this is a spring from a fixed point C1. Now we need to firstly define the points that are fixed in our system, that is the origin O here, the C2 point and the C1 point, and then we need to locate the points that are moving relative to these points. So we have M1, M2 and M3, and therefore we have three particles. So our state vector will contain each particle x and y direction, and then we'll have a last coordinate theta, which defines the rotation of this disk, and we need to add constraints on it, such as it rolls without slipping. So the first constraint is about the dimension of this. So this distance should be a constant, and therefore its square should be a constant. Now its square is just the scalar product of M1 with itself. So we need to add this to the constraint since it is a constant dimension, a constant value. Secondly, M1, M2. So we need to define this constraint actually as a function of the parameters of S. And as you see, OM1 times OM1 is just x1 squared plus y1 squared. And this one is just x1 minus x2 squared plus y2 minus y1 squared. As you see, the goal here is just to express this constraint as a function of the parameters and the state vector. Of course, this is S of t, and this is x1 of t, y1 of t, x2 of t. Everything depends on time and other parameters. Of course, I'm not gonna, express that verbally. Anyways, so this distance should be constant, and this one too, and this one too, C2, M3. You should define OC2 and OC1 prior to all this business. So maybe you would go like OC1 is equal to maybe 1, 2, whatever, and OC2 should be equal to, I don't know, minus 3, 4, maybe something like this. It doesn't matter, you need to define it. In this case it's slightly different, but you get the point. I'm gonna define this later. Now this is these are the three constraints about the dimensions of the system. This one, this one, and this one. But you still have another one, which is this distance should be always a constant. I mean, I shouldn't drop this as this position and then this point just goes down. I don't want that. I need this distance to be constant, and it's actually the radius of my disk. I mean, the PC or the Jacobian does not know that this distance is constant. I wouldn't say it's just a disk and leave it there. I need to specify that this distance is always a constant. Now, what should I do? Well, we need to add that d is a constant, and therefore d squared is a constant. And according to the Pythagorean theorem, d squared is nothing but b squared minus a squared. Now, b squared is this, is the scalar product of M3, M2 with itself. A is a little bit more confusing. It's just the scalar product of M3, M2 on M3, C2, but we should divide by this length, since the scalar product of two vectors is nothing but, it's their magnitude times the cosine of the angle between them. So if you want just this part, you need to divide by the magnitude of A. And that's what I did there, and the square, it just becomes the scalar product. Now, you can verify this for yourself, but this is it. Now, b squared minus a squared, I mean, it goes in that direction. I'm sorry, it's not this way, it's that way. And then b squared minus a squared is nothing but d squared, which should be here because it's a constant. Okay. The last thing is the rolling constraint. And now I need you to focus a little bit because this part is a little bit ambiguous. You know, just think about it a little and it will just appear to you. So theta is the angle between a fixed point here, maybe this one or that one, maybe with the black. The point is it's an angle that revolves with the disk. So we need to know that this distance, I mean, if this distance becomes bigger, then d is a constant, which is the radius of the disk. So d times theta should also become bigger. So theta becomes bigger, and this is the proportionality constant. It's d. So we need to have theta d minus a. It should be equal to a constant. Now I don't know if it's theta d minus a or theta d plus a. It depends on the orientation. Personally, I set it up to display when I solve the differential equation and all of that. I display my solutions graphically, and if I see that the dot is moving that way and the disk is rolling that way, I know it's alternating, and then I go back and switch the sign. It doesn't matter. I really keep it minus, and then I come back to change it. So yeah, there you go. Let's keep it theta d minus a. Now we have d here. I mean, it's just the square root of this b squared minus a squared, and a is just the square root of this. So yeah, it's really simple. We should add it to the rolling constraint. Now, when you set up the constraint, you can then derive the Jacobian. Of course, you derive with respect to x1, y1, x2, y2, x3, y3, and then theta. You don't forget that, because the Jacobian is the derivative of the constraints vector with respect to all the parameters present in the states vector. And therefore, I made a little Mathematica program. Let's just change the colors here to not hurt your eyes. So I defined firstly the scalar product between two vectors, and you get which takes as an input two vectors a and b, column vectors, of course, because we just work with column vectors. I hate working with row vectors. A and b, transpose of a dot b. Yeah, by definition, it's that, because here it's the matrix multiplication. So the transpose of a times b, and it takes the first element of that, since this alone will just output a scalar inside a matrix, and we need to take out the scalar. Of course, the auto scalar product of a vector is just the scalar product of the vector with itself. I define an impulse here because why did I define this impulse? This impulse is just a signal in this form. It just takes c and b as parameters, and it just outputs this function. This is t, and this is impulse of t, c and b, because yeah, b is a it's a characteristic of this width. Of course, b defines this function. It's the exponential of whatnot. I don't know. You can just find it on Google. It's just such as the area underneath it is equal to 1 or something. I forgot. Anyways, it's just an impulse. It's so I can give an impulse to my system, because I always have problems defining the initial conditions for velocities. I cannot really give any initial conditions for velocities. I can give some initial velocity to this point m1, but I don't know how to calculate the initial velocity for m2. I don't know really, and it should be and it should be according to my constraint. So I don't know what to do with this, and therefore I just keep the initial velocity equal to 0, 0, 0, all of that, and then I set up my my initial positions according to this. Maybe this graph, maybe if this is 0, 0, then this is minus 110 or something. This is minus 66 something. You get the point. It's just the initial conditions. They don't matter a lot, but therefore I do them close to the position of equilibrium, and then I give an impulse to this. I add it to the force applied on it. So it takes an impulse like that just appears for 1 second, then goes, and therefore it's not a continuous force on my system. It's just an impulse that gives it an initial velocity, and that's it. So that's why I defined this this impulse. Now this is Tawla of v. In my language it means the length of the vector v, and it's equal to the square root of the autoscalar product of v with itself. It's by definition this. I mean, this is the length of a vector. Now I didn't use length because it's